Okay, should we just get going? All right. So yeah, I hope all of you got the email in time about canceling the class, but I couldn't get back to town. The flight got canceled, a Midwest blizzard and all that stuff. But okay, so we'll have to have one more makeup sometime later. This was scheduled anyway, and thank you for coming over here. So I'll essentially get back to where we were, and if you remember, what we were really doing was looking at what would be the kind of the first thing you learn in a quantum mechanics course, where you solve Schrodinger equation and you get solutions for allowed energies in a particle in a box sort of problem. And here what we did was we looked at the infinite box problem first, where the barriers were infinite, right? And we get a nice closed analytical formula for the allowed energies. And the main reason for talking about that was to get a feel for what sort of numbers are we talking, what do we get in standard compound semiconductor heterostructure devices. So typically the barriers would be of the order, not infinite, but of an electron volt, or 0.3 electron volt, or hundreds of milli-electron volts, or a couple of electron volts, depending upon what particular semiconductor you'll choose. If that is thought to be very, very large, then the ground state energy, or the first energy level that is allowed, which is not zero anymore because your wave has to fit, and the energy allowed, if your quantum well width, the particles, the box size is 10 nanometer total, then LW would be 10 nanometer. Effective mass is 1, and if you plug that, then your ground state is at 3.7 milli-electron volts, right? And so this is the scaling rule. It goes as 1 over square of the quantum well and 1 over the mass. So the lighter is the mass, the higher is the ground state level, right? So the lighter is the mass, the higher is the ground state level. The thinner is the well, the higher as a square. So it's very, very strong dependence on the quantum well width, right? So that's and typically, as you can imagine, if you had a 1 nanometer well, this would be 376 milli-electron volts, and so on, right? So that's how it's going to scale. So then what we said was, well, typically my situation is that it's not an infinite well, but it's a finite well with a height of, say, U naught, which is is a few hundreds of MeV or an electron volt. Now, what are the new energies? And to find that, again, we go to Schrodinger equation. I kind of pointed out how you solve this equation, and essentially what you are always trying to find are the allowed values of k's, which are the 2 pi by wavelength, and I'll actually sketch this first, but let me just summarize. You're finding allowed values of k, and you have a differential equation, which is a Schrodinger equation. And what you're doing, the way you find those allowed k's that will fit, into the well, are you basically match the boundary conditions, right? I mean, that's the whole game. So you match the value of the wave function on the left here, which would be e to the power ikx and e to the power minus ikx's with certain unknown coefficients, and here, which will be a decaying function as e to the power minus some real constant time x, right? And so here, so you have 4 unknown coefficients, one tail here, one tail there, and a sinusoid inside. And you have 4 unknown coefficients. You can essentially, to get a self-consistent solution, you must have a relationship, between k, an equation for k. That's the determinant, right? Yeah.
Should there be a minus sign in that first dimension?
Oh, you mean here?
No, one up.
Here?
Yeah.
Yeah. So actually, you can always justify what it is, because it's minus x here, So yeah. So x is negative. So it's always decaying. Just use your physical intuition that if x is negative, then to have a small number here, it should be. Yeah. So and then we get this thing, which is I'll actually discuss that now, and it has. So essentially, your equation looks something like this, right? And now you've got to find the k's that are allowed. And whenever you get an equation like this, it's kind of nice to always non-dimensionalize the entire problem And that's where we were. We were just discussing that in the end of the last class. Okay? And the nice thing about this infinite well problem is, I'm going to just switch this off for a little bit. Okay, so how do I blank this? Okay, he won't go away, right?
What you can do is make a pure black slide.
Oh.
Display a black slide. Effectively the same thing.
Is that the only way?
It's a trick. It's a cheap trick.
Okay, let me try. How do I do that? That's going to take.
Oh, there you go. No, I was sleeping at my ear.
Oh, just sleep it. That's actually not a bad idea.
It was blue.
All right. So a black slide. Okay, no, there must be a blank here, right?
Yeah.
No, it's back. All right, I'll just switch it off. It's okay. We'll come back to this. Or I just try this once, right? How do you make a black slide? Insert like a little box of.
You need a new slide.
Sorry?
You can make a new slide and then change the background color to just pure black.
Okay. All right. I know what you're saying, but I have all this, frame and everything. So, okay. Everything is always hidden these days. It's never clear, right? Wait, it's not even black.
It's at the top.
Okay, there you go. Yeah. It's working, yeah?
Oh.
It is working, right?
Mostly.
Okay, good. Okay, good. So, nice. All right, so, right, so again, I mean, just trying to summarize this problem primarily because it's kind of an important problem. So, right, so you have a height of u naught, typically a electron volt order of magnitude, and then you have these particle potential barrier height, and the width, let's call it LW. In the textbook, Rocket's book, he says from 0 to L and 0 to minus L. So LW is twice L and all that. So, and the equation is really the Schrodinger equation. We are looking at the one-dimensional problem, and I will is equal to E psi of x. Right? So, so you notice that V is actually flat here and V is flat there. So essentially, you have a V is 0 and a V is equal to U naught. So really, nothing. It's just a step here, right? That's what it is. And so in general, whenever you have a constant potential, the solution of this equation is you can write it for the 1D Schrodinger equation is always 2 times whatever is the mass you have there over Planck's constant squared times okay, so we take this over there, V minus E, right? Oh, sorry. E minus V of x, sorry, minus E, one of them, right? So times psi of x. Right? So you can see whenever it's flat, it means this thing is constant, right? If this is constant, you see in nature of the equation, the curvature, meaning twice, you're taking twice the derivative, you come back to itself with a constant in front, right? So that means it's an oscillating function, right? Always, whenever it's flat. And then so you can write psi of x is equal to some a constant e to the power I k times x plus some other constant e to the power minus I k times x. It's a linear superposition, and this will always satisfy this equation. Right? That's the guarantee. Now, if this term is actually, tell me, is this correct? Should be v minus e or e minus v? Is correct? Okay, good. So you see now, if this term is negative, what does that mean? It means the energy of the electron, we are looking, remember these are all potential, or rather these are all allowed energies. If there was no barrier like this, all these energies would be allowed. Right? All of them would be allowed. And now we're saying we have added a barrier like this. What are the new energies allowed? So if I kind of start looking at all energies now, then basically this equation is dictating what are the new energies allowed now. So see if solve this and say, well, if it satisfies this equation, it's allowed. Right? And the E, if it is negative, what does that mean? It means that if I'm looking at this point in real space, the energies are here, but that's really not, that's well below the minimum potential energy. So the energy has to be higher than that. So we start from here, and let's see. So if no, what did I say? If this is negative, the whole quantity, it becomes a negative some number, right? And your equation for whenever you have double derivative is negative times whatever times that function, you have basically sine kx's and cosine kx's. This is the solution, right? Of this is an oscillator equation. On the other hand, when this becomes positive, it switches sign. When is it negative? For example, if the energy is here, you see the energy, E is this one, but V at this point is this. So V minus E is negative. E is larger, right? So that would be an oscillatory equation, meaning it's going to go like sine, or cosine or a sine. We kind of talked about that, right? In that region. But for that same energy, when you enter this region in space, you see the switches sign, right? So this goes positive, right? And whenever you have double derivative is equal to positive something times itself, you always have what are sine hyperbolics, x and cosine hyperbolic. What is it? It's exponentially rising or exponentially decaying. So that's the meaning of it. So it switches sign. So essentially, instead of sines and cosines, I can write it always as e to the power ikx is the nature of the solution here. Here it's basically some kappa, which is times x. Essentially what happened is this k became imaginary. The wave vector became imaginary. So, right? So an imaginary times I becomes real. So it could be plus or minus depending upon which region of space you are in, plus or minus whether it's going to the left or right and all that. Right? So that's the nature of this any quantum mechanical problem. And here, both the real part and the imaginary part in the compound semiconductor devices play a huge role. I mean, very important role. And the reason I'm going through it again now is to talk a little bit more about the imaginary part of it, which is the decaying part. And that is actually a very important part as well in realistic usage of compound semiconductors. The decaying parts where this is real, meaning, sorry, when that thing is positive or the k becomes imaginary. So essentially what that means is your wave function has a nice sinusoidal function here, but the moment it enters here, it must decay exponentially. That much is, so it must go down as e to the power minus kappa x. The wave function must go down like that. What is that kappa? Do I know that? How do I know that?
The boundary condition.
Right, yeah. Right, normalization, but actually, you're right, you apply, but actually it's a solution to this equation, right? And let's kind of dissect it one by one. Kappa, what are the units of kappa? That's always, the first question we should come to. What should the units be of?
1 over length.
1 over length, right? So exponential of anything must be dimensionless. 1 over length. And now, you see there's an equation here, wave function, let's say whatever dimension it has. I'm not particularly interested right now. But all this object sitting right in the front here, what are the dimensions of that? Looking on the left side, I have 2 lengths in the denominator, right? So this whole thing must also be 1 over length squared, right? No matter what that quantity is, it must be 1 over length squared, right? And so, and I'm basically just going to say that you can plug in this value, this sort of a wave function here. When you take double derivative, what it does is it basically pulls this out twice, right? You get kappa squared, right? And no matter what are the details of the function, it's going to pull out that kappa squared. So here's the formula for kappa. Kappa square is equal to this whole thing, right? Sitting in the front, and therefore kappa is square root of that whole thing. Agreed? I mean, that's what it is. It has to be that. I mean, there's no other. This is the characteristic length in the problem, so it must be this, right? So yeah. Now this is something, again, you must have intuition for in compound semiconductor device design and all that. Okay. So okay, V minus E. So V0, or sorry, U naught minus E. So here V of X is U naught, right? And energy is E. So if an electron energy is a bound state, that is okay. So what is this telling you? No, in electromagnetic theory, you know that when light is incident on a metal, for example, right? Light is incident on a metal. Light actually gets reflected, but it actually does penetrate a little bit. Right? That thing is called the skin depth, right? Skin depth. It does penetrate a little bit, depends on the conductivity of the material, etc. It's exactly the same thing here, except now particles are incident on the wall, right? This electron is rattling back and forth. It's incident, and this is the skin depth of it. 1 over twice kappa is the skin depth of this problem, right? So effectively, it's a quantum mechanics skin depth. And what is the order of magnitude of this? You can plug in all the numbers. This is the effective mass, and these are electron volts and all that. Okay. So let me just write down, just like we did for the energies, the order of magnitude of this problem will be 1 angstrom, and then there'll be a square root here, obviously, again, and m star over m naught, which is the free electron mass, and this u naught minus E, whatever that is, over 1 electron volt. Does that make sense? This is the dimensional unit of the problem, to get a feel for what are the length scales here, right? So if your effective mass is 1 and the barrier height minus the ground state, remember, we are not talking about u naught. We are talking about u naught minus this. And that is also very important. I mean, actually, within the next 10 or 20 minutes, I'll explain why is that thing important. Meaning, we are not talking about this entire thing, but only this part. If that is 1 electron volt and this is 1, then your, this essentially kappa, the length that it kind of decays over, is 1 angstrom. Did I? Wait, did I do that correctly? Kappa? Yeah. I mean, rather, this is all correct. I'm just saying that I wrote this correctly, right? Kappa is 1 over length. So this is 1 over length squared. 1 over length squared. Yeah. Okay. Good enough. Yeah. So you can see from here, first of all, does that make sense? I mean, if physically, if it doesn't make sense, then there must be something wrong. Physically, if my u naught is very high, should it be 1 over that, right? 1 over that?
Yeah.
So, yeah. So I was just wondering, because physically it's not making sense to me. So
the other one was.
Oh, yeah. You're right. So u naught minus E. You mean this part, right?
Yeah.
Because I see. Because you see, kappa is 1 over length. This can't be 1 over length. So it's this whole 1 over this whole thing. Yeah. Okay. Good enough. Yeah, that was bothering me. What's wrong there, right? Okay. Right. Does that make sense? Because no. Okay, let me rewrite it. Because I know what's wrong, so I'll just rewrite the whole thing. So there's kappa. So it's basically 1 over. That is kappa. Let me introduce, just for simplicity, another term, which physically would be the skin depth here. See, if your wave function is going as e to the power minus kappa x, then wave function squared, which is more indicative of the location of the electron, right, mod psi squared, is going as e to the power minus 2 kappa x. And I pull this 2 kappa and call it 1 over the skin depth delta. Is that fine? I'm introducing a physical quantity called a skin depth, where delta is the skin depth. Okay. Right? And now let's write down the formula for skin depth. Obviously, it's related, and it's in a simple way, to kappa, right? 1 over 2 times that. So you turn it all upside down now, and you see it's, h bar square. Well, yeah. It's the uninteresting part of this algebra that takes the most time. So anyway, okay, so that's the formula, right? The skin depth, but actually because it's 2 here, I take that 2 in, it becomes 8 here, right? Inside the square root. So that is the quantum mechanical skin depth for a heterostructure, or actually any problem. I mean, it happens where we are in a compound semiconductors class, but this is a very general problem. So, and now if you plug in all these quantities, now you get 1 angstrom square root of 1 over m star over free electron mass times u naught minus e over 1 electron volt. Okay, so that makes sense to me now. So because what does that mean? It means that skin depth, or the electron penetrates into the barrier, the heterostructure barrier. If it is, the barrier is high, the penetration is low, right? If the mass of the electron, effective mass of the electron is high, it doesn't penetrate too much either. So that's the other very important thing to see. So those two are the important quantities here. And for effective mass of 1 and 1 EV barrier, effective barrier height, the penetration is 1 angstrom. Right. Now, we know from this problem now that there is another level here, right? Let's say there are 2 bound states in this problem. For the second level, which one will have a stronger penetration into the barrier? Second one, that's clear, right? Because this term is, and you can see as you go higher and higher, those states, if they're occupied, kind of, make it further and further into the barrier, the barrier set. Yeah? And then that is also a very important feature of compound semiconductor heterostructures, where you design structures. First the ground state. If your transitions between ground state, you see mostly just the quantum well properties because the penetration is very weak. But if you start seeing transitions for light or whatever from higher occupied states, you start seeing some properties of the surrounding regions, because those electrons are not, the cloud is kind of sampling a larger part of the barriers now. So it's for the higher excited states. Yeah.
What happens if E equals mu naught?
Say that again. At E equals?
At E equals
U naught, yeah. So that part we kind of just had started discussing towards the end of the last class, and let me explain that part now. Meaning, when it becomes just not bound, it becomes, you're talking about a state where you're like here.
Yeah, like
yeah.
Right at
so I'm this way. So the way to actually solve this exactly, remember I said that is essentially just do a matching of boundary conditions and all that, right? And in region 1, 2, and 3, 1. Region 2 and 3. This is, by the way, I have almost written off your second assignment, so this you will, solve and to your heart's content, I think so. Yeah. Okay. So in region 1, you have e to the power kappa x. In region 3, you have e to the power minus kappa x, right? And region 2, it looks like you can write e to the power ikx times plus c to the power minus ikx. And d. Right? Psi in region 1, psi in region 2, wave function in region 3. This is basically just wave matching again, right? And then at plus L and minus L, at these 2 points, you just match the 2, right? And then match their derivatives as well. And once you do all that, the upshot of all this business here is you're going to get equations that you need to solve in K, right? To get the determinant, for example, right? So to eliminate ABCDs to get the non-trivial solution. And the equation is essentially going to look all right, so it's going to look 0 square. Let me write it in this way, minus cotangent of theta. So there will be 2 branches for even and odd solution, sinusoids here. And what is this theta? This theta is basically allowed k, that you are searching for, times the length of the well over 2. That's your theta. This is all also in the slides and done in Rocket's book, so I'm not kind of trying to stress through. This is exactly what you're going to get. And this theta naught is a non-dimensional parameter, obviously, right? And it depends on u naught and h square by, I think 2 m star LW, m star LW squared. I mean, something like that. There may be a factor of 2 I'm missing here, but I don't want to bring the slide down right now. Just something like that. Okay. So that's a non-dimensional parameter that depends on all the physical quantities that you're feeding into the problem: the quantum well width, the barrier height, and the effective mass. These are the only 3 parameters in the problem, right? And it captures all the physics is inside there. And then on the right side you have that. And this equation is actually a very interesting equation. It appears in so many problems. Yeah. Okay. So I'm going to erase this part. So remember the skin depth. It's a useful parameter, 1 angstrom and all that stuff. So I'm going to just erase this part. And when you are going to solve this, obviously many ways to solve it. And as you can see, it's what you call the transcendental equation. It doesn't have an analytical solution, right? Tan of theta is equal to some, square root of that same thing. So that has no analytical solution, right? But you can ask your MATLAB or Mathematica, whatever, to solve it numerically. But pictorially, you can sketch it, and that's what we were kind of sketching last time. And I wanted to do that again just to illustrate a few points about this problem, which are sometimes not stressed again in typical textbooks and all that. Okay, so what are we plotting? We're going to plot versus theta, which happens to be KL over 2. K is what we are searching for. We are going to say, all K's. Right now, this is the axis for K's. Here's the quantum well width, right? And we see on the right-hand side you have tan thetas and cotangents of thetas, right? So we know that those things actually have intersections at pi over 2, pi, 3 pi over 2, and 2 pi, and so on, right? So, and tangent goes. We discussed that, right? Tangent blows up at pi over 2 and comes back up again, and all that kind of things. Cotangent is kind of going to do that. Now tangent again is going to do that. Cotangent. So you have all these nice looking functions going on like that. So this is all right hand side, right? This is all right hand side. So I plotted minus cotangent, not plus cotangent. And the left hand side is a strange looking function. It has square root of 1 over theta square minus 1, right? So you know right away that there is a critical point in the theta axis which happens to be exactly related to all these physical parameters, beyond which, if theta becomes larger than that parameter, this thing is imaginary, right? So at least it's not real. And on the right hand side everything is real, so the equation will not be satisfied. So beyond this picture, there are no thetas allowed, meaning that the k's corresponding to this beyond that is not allowed. So that's the critical value. And then beyond, under that, you basically have a shape that would look something like that. You can plot it, right? It looks something like that. And when you're looking for solutions, what are the solutions when the left-hand side is equal to the right-hand side? So here's the first solution, there's the second, here's the third, and that is it. You have only 3, right? Does it make sense? So that means for that particular theta, this quantum well has exactly three bound states, right? That's how you counted it. And now how do you find the energies? Well, go down here, find the value of theta. That immediately tells you k, because you know your quantum well width. Do 8 square, k square by 2m star. That is your energy. That's the allowed energy for that. Similarly, here's the second one. Here's the third one, and that is it. The three bound states, and what I've sketched, obviously, right? So I'll give you some where you play around with it. Now that's all good. So you counted 3. You can actually write down exactly how many bound states will be there in any quantum well. There's a formula for it. If you want to find how many, so it will look like 1 plus integer times some parameters, which will have this theta naught and all. I'll ask you in the assignment. There's a formula. Plug in, it'll tell you you have only 4 bound states. You have 2 bound states. But in a 1D problem we had discussed, you can see right away you will always have 1 bound state. And when I'd asked that last time, right? So you will always have 1 bound state, guaranteed, if you have this situation, because this is starting from 0 and this is going to 0. I mean, they have to intersect at some point. There's no way out, right? So you'll always have 1 bound state. And so therefore you always have 1 plus something. We said this part can be 0 at most. Some other parameters you see very interestingly. Let's imagine we increase the barrier height towards infinity. What that is doing is it's not changing the right hand side at all. It is leaving it like that. What it's doing is taking this thing more and more towards, stretching it out. Right? So you have more and more states. Right? As you stretch out and make it deeper and deeper, meaning choose a higher conduction band offset here, for example, between the two materials, you have more states. Not only that, what you notice is this point is moving closer to asymptotically closer to this pi over 2 value. Okay? It's moving closer. Right? The intersection point. Similarly, this intersection point is moving closer. You know, whenever U0 is pulled up, basically you kind of go like that. So this point gets close to this point gets close to this one goes close to this, and all that. So what happens when this point, when U0 goes to infinity all the way, right? So basically all the intersections are at pi by 2, pi, 3 pi by 2, 2 pi, and so on. You can see that right away. And what you get back the infinite problem solution. Right? If you just take theta is equal to pi by 2, plug it in here, right? You see right away what is your ground state K. It is, you know, pi over LW. Remember we did this in class. This is the ground state wave function, right? The one that fits exactly like that. Make sense? So it just merges with that solution, right? Yeah. And that's nice. And it should, I think, I mean, there's nothing fancy mathematically. This is how it should be, right? What else can we say? I mean, whatever we are talking about in terms of the barrier height, you can do the same thing with things like effective mass. You can do something with the quantum well width, right? Quantum well width, as it grows wider or smaller, you know, if your quantum well width becomes very small, you can see theta naught goes up, so this thing gets stretched out again. You have more bound states, you know. And then what does you see quantum well? Actually, is that correct? If quantum well width gets shorter, a squared k squared. See, I was wondering. Okay, you see, this formula is not right because intuitively it makes no sense, right? So let me correct it. A squared by 2 m star LW squared. That's how it should be, at least dimensionally. This is correct. LW should be here. So what does that mean? If quantum well width gets very short, theta naught gets small. Right? And if for the same barrier height your quantum well gets shorter and shorter, what happens is this gets pushed up and up. You have less and less bound states left. Right? You basically squeeze out the bound states, and so on. So we can kind of picturize many of these using this picture. Okay. Now, what I will sketch now is a picture of this problem as a function of the quantum well width, and we'll kind of take it from there. Okay, so any questions on this? I think I'm pretty much repeating it, but it's probably fine. Yeah. Any questions? Okay. If not, let me then come to this picture here, which essentially whatever we discussed now. Again, you know, the lower is the ground, the bound state, the smaller the distance it penetrates into the barrier. Very important. Right? The higher is it, the larger the distance it penetrates. It's not kind of clear here, but if you look at the numbers, that's how it is. And then there's skin depth. Order of magnitude, 1 angstrom if you have 1 eV barrier height and free electron here. 1 angstrom penetration of order of magnitude. Now, if you have such a situation, we know that these are atomic-like states now. These electrons are atomic-like states. But in reality, the way we are going to realize a quantum well in a semiconductor is in multiple ways, but I'll start with a situation which I had mentioned in the last class, where you have a nanowire, for example, or a nanotube, where the electron is really not free to move radially, but it's free to move only in one direction, and then you put 2 narrow bandgap materials in its way, right? So then you get here, one narrow bandgap material in its way, you get a single quantum well, right? That's the picture. But it's actually also free to move in one dimension, even when it's not inside the well. It's, when it's outside the well, that's a continuum state, right? So what are the energies allowed and what are the density of states allowed? That's what this is showing. Okay? remember, if you had no quantum well, if the barrier height was, or rather, instead of a barrier like this, if you had this thing was flat, right? There's no potential well like that, right? And then the electron is moving in one dimension. We have already found the 1D density of states. It goes as 1/square root of energy, right? The moment you introduce this, now we know that we have introduced some bound states. In this picture, there are two bound states depending upon the problem, right? And then the two bound states. But there's also a very interesting theorem in basically which says that the total density of states is always constant, right? So if you have introduced 2 points here, two bound states here, you have taken away some from there. Okay, so there's a little less outside now. I'm not proving that's all like in a solid state physics or a quantum course you would prove that. But you see that if your energy is much higher than the barrier height, here the barrier height is about 0.3 electron volts, meaning this U0 is 0.3 electron volts. If your electron energy that's being injected and going in that wire if the electron is going at that energy, then at that energy density of state is kind of there. If it's as you go higher and higher energy, you don't see the well. It looks like you're in 1D material, and that makes sense. I mean, you're really barrier height. Your kinetic energy is way higher than this potential well, so you don't see it. Right? And that also makes some physical sense. So this is the real density of states. You have this, and then it has this oscillations in energy, and then it dies like that. I mean, it merges asymptotically with the free electron. So that's how it looks. So that's the density of states. So that's one way of realizing the quantum particle in a box problem, but in reality, the way it's most of the time realized is not in when an electron is free to move in 1D, but it's realized in three-dimensional solids like in gallium arsenide or aluminum gallium arsenide and such materials. Right? And the situation is such, again, I mean, what we are showing here is like a photoluminescent spectra, and I discussed that. As you squeeze the well, the energies float up, the ground state's energies float up, and you get, shorter and shorter wavelength energy. D is, for 2 nanometer barrier, 4 nanometer would be C, and, so on. So you can control the, so what are we doing here? We have a quantum well for conduction band. We have a quantum well for valence band too. And you have quantization going on in both. So you apply your H square, by m star, but m star of the conduction band here, m star of the valence band here, and you calculate where is my ground state of holes, hole 1, hole 2, second level, and electron 1, electron 2, and then there are transitions between those, and that's what we are picking up in spectrum. Right? Okay, so instead of 1D, if you have realized this whole business in a three-dimensional crystal, where you put a very thin sliver of quantum well, which actually I had shown you the picture earlier. Here are the atoms. This is not gallium arsenide, but gallium nitride. This part is gallium nitride. It's hard to see in a TM, but maybe you can see a very slight color contrast. And this is about, roughly about, 1.5 nanometer quantum well of indium gallium nitride. So here, the dots here are actually nitrogen atoms you can't see. What you're seeing here are gallium atoms. What you're seeing in between here, indium, and then gallium again. And so this is a cross section. So essentially, it's everywhere around in this plane you have atoms. I mean, it's a periodic crystal. It's just that little thing which is the quantum well. So it's actually a 3D solid, and inside it, only when the electrons are moving in that direction, you have a quantum well. If they're moving out of the plane in gallium nitride, they don't see any quantum well. Does that make sense? I mean, so it's a well like in one direction, and if you're going this way, you don't see it, right? If you're parallel to it. So as a result, your density of states of the rest of the electrons that are not moving at along perpendicular to the well will look like a three-dimensional. It's a square root of energy, not 1D. Does that make sense? I mean, it depends on what solid you are putting your quantum structures into. So your continuum will be 3D in that situation, and then you will get the bound states. And I'll discuss that now. Those are called quasi-bound states, or they're not they're not discrete states, but they have sub-bands. That's the meaning of that problem. So I'm going to discuss that now. Okay, so any questions on this? I think I'm going to just follow up on this. But any questions? Yeah.
If the transition is non-radiative, can we measure that?
If it's non-radiative, you won't see in the luminescent spectra. Yeah. So and there are all aspects of selection rules, meaning you have transitions which will occur only if certain symmetries are allowed. But I've not discussed that yet. But if it's non-radiative, you won't pick it up in a luminescent spectra for sure. But maybe there are other ways to pick it
But
up.
we still can measure it.
A non-radiative transition?
Yeah.
Indirectly, because if it's non-radiative, the question is where is the energy going? If it is going into phonons or heat, then you got to detect the phonons or heat, right? So, and you do Raman or something like that, which pulls, measures the phonon occupation instead of light occupation, and so on. So, yeah. Okay. Your question?
Okay, I was just like wondering what other transitions that would be non-radiative.
Oh yeah, most of them are phonon related, meaning the energy has to go somewhere,
Yeah.
right? And the energy either goes into light or it is going to heat. And heat is basically crystal vibrations, and it can. Yeah, so I'll discuss that part sometime later when we look at lasers, because when you inject electrons into this well, you inject electrons that will start out here and they have to fall into this ground state. And all that energy in falling goes into heat. No, not in this sort of structure. On the other hand, you can make other sorts of structures like quantum cascade lasers where, when you transition between, I will discuss that later. So primarily the energy dissipation paths are two. One is light or heat. And heat typically in semiconductor devices, we're talking about lasers, LEDs, is irretrievable. It's a loss, typically. Right? But some devices you can turn it around and make use of it, so thermoelectrics or some other things like that. But typically here it's lost. Okay, I'm going to talk a little bit about subbands before I move to the next thing. So I'm kind of looking at all kinds of. So we looked at 1D, but now we're going to look at a quasi 2D system. And let me explain now what we are talking about. I just mentioned that instead of 1D, let's say I take aluminum arsenide and then I put a quantum well of 0.3 electron volt deep. But it's a whole layer of it, right? It's a whole layer. And then again, that quantum well, only if electrons are moving in this direction, all these bound states occur. Right? We just talked about it. Only if it's moving in that direction. And then now this is a little more accurate. You can see the penetration or the skin depth here. For this state is much smaller than this one, and this is really spread out, right? You see that it's kind of twice the well, really, right? The shallow levels. Yeah. But if the electron is moving at an angle, and especially if it is moving, in that direction, which is, let's say this is z, and if it's moving in the xy plane, it is a free electron. It has no potential barrier, no quantum well, nothing like that, right? And a free electron has energy, which is, kinetic energy, which is above the potential barrier. So let me write that down. What you see here are these bands. Instead of a discrete level in the quantum well, you see a full band here. But the minimum of the band is exactly equal to the ground state of the single quantum well. What does it mean? Only if it moves in z direction, it basically has to get stuck. If it has energy this much, it's going to get stuck, right? I mean, it's a bound state. But if it's completely free to move in the other two, so therefore it is like a free electron parabola, h squared k squared by 2m. Here the k is perpendicular to this. It's not in this direction. That, if you understand this point, is going to make your life very easy for the rest of the devices, the rest of the course. Actually, a lot of things we're going to talk about. That quantization in most structures is only in some directions and not in all directions. The only situation where you have quantization in all three directions is in an atom, a hydrogen atom, which is why you have perfectly discrete states. You can coax some atoms to behave like and combine and form a crystal and behave like an atom. That's the nanocrystal, sometimes called nanocrystal quantum dots, right? You have 40 atoms or 100 atoms. But if you look at the spectra, there are some bound states which are looking like, even, like a really atomic-like spectra. But then the moment you have that above the, some band energy, it's going to become a, 3D again, right? So this it's called a quasi 2D system now, because if you're bound here and the electron energy. So remember what we're saying. This is the minimum energy for the electron if it's in the ground state. Being in the ground state, it can still move laterally. If it is not moving at all laterally, the kinetic energy because of lateral motion is 0. Then you are sitting here. This is the state. If it is moving pretty fast, even being in the ground state, you can be here. You can be actually higher. You can have a higher energy being in the ground state subband than the first excited state. Does that make sense? you could be moving pretty fast in that direction, and your energy could be larger than this ground state of the second subband. These are called subbands now. Okay? And all the kinetic energy, because in this here, is because of lateral motion, lateral to the quantum confinement direction. Does that make sense? And once you understand that, you can write down all the math and all that. That is not very difficult, but this part is, qualitatively understanding it sometimes is sometimes skipped in books. So we just skip. Okay. Yeah. So we'll now just quantify this a little bit, and this is working out nicely. So we'll just quantify this aspect of this quasi 2D systems. And the quasi 2D systems are really at the heart of pretty much every transistor we use today, like a silicon MOSFET has a quasi 2D electron gas. HEMTs and lasers and LEDs, all of them have quasi 2D systems. So that we use today. Okay, so in terms of the energies, let me just say that in general, I think I just write it this way. In general, what you have is three-dimensional Schrodinger equation plus V of R. Sorry, E psi, right? In general, you have that. But I think we don't need to kind of go into all details here. But essentially, what we are saying here is, if in the z direction I have a quantum well, but everything in the xy plane, it's hard to this is potential now, so I don't want to kind of plot axes. But in the xy plane, there's nothing. Right? I mean, it's all uniform in the xy plane. In that case, you can see that this equation kind of decouples very nicely into three parts. If I were to write the wave functions, I mean, that's really what I want to make sure that you have a feel for. In the z direction, because of these quantized states and all that, your quantization will give you like a sine, n high over quantum well width sort of wave function. This is your ground state wave function. These are the wave functions for the z direction motion. Makes sense? I mean, these are the signs, and even, odd, and all that stuff. This is what it is. Actually, I think we should have cosine because our anyway, I think you understand this. So if your z is 0 here in the middle, and you have plus L and minus L, and so on. So this is how it looks roughly here inside the well. Let's look at infinite case again for simplicity. But this is only the wave function for the z direction motion. Right? You always have, it's a three-dimensional wave function. It also has x and y dependence. But what we're saying in this situation is the x and y are free electrons. And free electron wave function, we know it's just a complex exponential. So it will look like e to the power I, kx times x, e to the power I, ky times y. Now, these are plane waves, a free electron wave function. This is the total wave function. Meaning, if you have solved your particle in a box, plop in the solution for that here, rest is all free electrons. And when you plug that into the solution, the V of R has nothing to do with x and y's. There's nothing in x and y direction, right? So all that this does is, this is gradient. It just does d by d2 by dx squared and d2 by dy squared. It takes all these things and sums them, right? And you can see if you take d2 by dx squared, you're going to pull out two ik's to the front, and it's going to give you essentially a h squared, k squared by 2 times effective mass. This is free electron momentum, kinetic energy. Momentum in the x direction squared by twice mass, right? So v squared, or half mv squared if you might. And then h squared, ky squared by 2 times effective mass plus, and this term is going to give you all these energies that you just calculated from your quantum confinement, right? N squared, squared, and all that stuff we just calculated, either by finite well, infinite well, whatever you have calculated. So your total energy of the system is actually, any direction that is quantized. So you'll always have, you can always think of, x, y, z axes. In the z direction, it will be indexed by a little, integer whenever it's quantized. Ground state, first excited, second excited, whatever it is. Right? The other two directions which are free are essentially continuous functions, right? That's what we have, and this is continuous. It's continuous. And that's so when I take this and I plot the energy now for a quantum well, which is made of a compound heterostructure that might look like that. It's a wafer. Typically, it will be growing in industry. People are growing at 4 or 6 inch of this, and then put a quantum well inside in one layer. So this part may be whatever narrower gap and wider gap and all that. So the band diagram in that direction is like that. Right? So now, if you plot the energies, let's say just for the conduction band, that's what I was showing a little bit earlier. That you have the ground state E1. E2, and these are your NZs. These are your NZs, right? But really, that is, if I were to plot my EK diagram, remember, I can plot it versus KX or KY, right? Or I can plot it, if your masses are kind of the same in both directions, you can combine them and say this is KX squared plus KY squared, and call it K perpendicular square, which is perpendicular to the plane of the quantum well. So that in that direction, your minimum energy. So this is the total energy. The minimum you can see is just the ground state energy here plus all this free, kinetic energy. So you get a parabola. So this is the first subband. First subband of energies, right? And similarly, you have the second subband and third subband. If you have 3 bound states, and then finally you will have a continuum, meaning above that, above the U0, which is the quantum well width, quantum well depth, you have a continuum of states now. So that's the picture. And now I can ask what will be the density of states now? So density of states as a function of energy, right? Now this is very interesting, and this is actually very, very important, right? Density of states below the ground state is always 0. There's nothing underneath that. Right? There's no energy allowed underneath that. So that is 0. And then, we're going to have all these points which are kind of important here. So and then when you hit this point, your density of states, how will it go? Will it go as square root? Will it go constant? Will it go like that? How will it go now? Meaning, what I'm really asking is, if I have an electron that is sitting in the ground state here, and it has this dispersion, for example, does it follow 2-dimensional, 1-dimensional, 3-dimensional dispersion? What dimensional? What is the dimensionality of motion for that electron? That's the question, right? So 2, right? It can only move in 2 directions because that thing is bound. It cannot go out this way. Only move in 2 dimensions. Therefore, the density of states will have a step, and we have already found the density of states of 2 dimensions is m star by pi h bar squared. That's going to be the density of states here. If you have spin and valleys and all that, you get GS's and GV's. This is something I'd done before, so please, look back. This is the 2D density of states. You have a step, and the density of states becomes flat, and stays flat till you hit the second level here. Right? In fact, the density of states of this subband continues to be just 2-dimensional. It remains 2-dimensional. It doesn't care, does that make sense? It's a 2-dimensional electron system. It just has a 2D density of states. It's a flat slab. The height or the density of states is just that. More is the effective mass, more is the density of states. But then what has happened is, by the time I hit this energy, I have another subband with exactly the same density of states. So I have a step in the density of states. It's going to step like that, and I have another subband. This is the second subband now, right? And so on. So the density of states goes through the staircase sort of features. Okay. Does that make sense? So this is the first subband, second subband, and third subband, and so on, right? Till you hit the continuum. Does that make sense? Or any question? And this is not just, actually, in the design of HEMTs and lasers, this plays a huge role. You have to play with the density of states in nice ways. Meaning you sometimes want very high density of states, sometimes you want very low, and you have to, you choose accordingly. The well width and all that, because the edges we'll see that the gain spectrum of a quantum well laser will essentially be a mirror of this. The gain spectrum will look something like that. We'll see that later. When you get, you have to offset the gain with loss with lasers. This plays a very big role there. The step-like function of the density states. And so as a result, in general, you can write for a quasi 2D systems like that, your density of states as a function of energy will be you're basically kind of summing over unit step functions that start out at E and Z's, right? And there's always this m star spin valley over pi 2 pi h bar squared. Does that make sense? You're kind of summing over energy. Makes sense? I mean, if you're here, there's nothing to sum. If you're here, you have only one of these, so you get 1. If you're here, you get 1 plus 1, that's 2, and so on. Right? So this is an analytical form for the density of states of a quasi 2D system. Okay. So let me again show you a little picture of this. Actually, how are we doing on time? 40 minutes. Not bad. Okay. Oh yeah, so I forgot to mention, but yeah, sure. So now these are the density of states, and as you know, I mean, we have discussed this. So as you start filling or emptying these states, you're moving the Fermi level. So if your Fermi level is in the gap, this is the density of states staircase for the quasi 2D system, and these are what I just mentioned. But these are the available states. They may be occupied or they may be unoccupied, right? So now you pull the Fermi level in somehow, either by injecting carriers into the well. For example, what I can do is have an N-type semiconductor here, apply a voltage, and try to inject and dump in a lot of electrons here, right? That's one way to move the Fermi level. Right? Another way is you put an electrostatic gate here, put an insulator, and then apply a voltage on that kind of a capacitor here, and that makes a transistor. So that's you fill states or empty states, make it on or off. That's a transistor. If you inject electrons, inject holes from the other side, that's a laser or LED. So if you move the Fermi level here, then you have only one subband occupied, as you can see. If your Fermi level is here, right? If your Fermi level is in between the two, you have only one subband occupied, right? And all the electrons have the same, Z part of the wave function. They have the same symmetry, right? The moment you pull it up here, you have kind of half the electrons, or actually the number of electrons in the subband is area under this kind of curve here, right? Every slab has its own area. So when you pull up here, you have a small number of electrons, which is the area of this little rectangle here in the second subband, and a large number of electrons in the first subband. Does that make sense? That's the area under the curve. These are things you can very accurately measure. For example, if you do magnetotransport, very high magnetic field, and low temperatures, you can start seeing oscillations of these, and you can actually detect there are two subbands. You can measure that very accurately. You push it a little bit more, you get these quantum Hall effects and all that kind of fun stuff with that. So, okay, and this has a lot to do with optical transitions and such things as well. Yeah. And just like that, we saw you have rectangular wells. But I hope you understand the meaning of subband, right? This is a very important point. Subband is very important. So, for example, instead of looking at 3D materials, let's say you started with moly sulfide or in one of these 2D layered materials, and then you build a quantum well, which is now a strip. Does that make sense? You have moly sulfide, and which is a 2-dimensional crystal. And then you put a little strip of something else, like which is narrower band gap, and then you come back to moly sulfide again, right? So now, how will your density of states look? Your free state is not 3D, but it's 2D, right? And then you have quantized, you put your quantum well in one direction, right? So what will it look like then? Meaning your density of state shape, how will it look now? Does that make sense, the question? Yeah, go ahead. Yeah, you will get a spike here because your normal density of states is actually become one-dimensional, right? I mean, the free motion is in one direction, so you get a little, but it's not going to be just like spikes. It'll spike and then it'll go down as 1 over square root of energy, because and then you'll have another spike. It'll go down. So that's the shape you'll get. And these are something you can do with compound semiconductors too. I mean, in fact, not you can. It has been done in great detail, and not just molysulfide and all. I mean, this has been done a lot in 80s, 90s, which is artificial low-dimensional structures. And you start with 3D, go to 2D, quasi 2D, quasi 1D, quasi 0D, and basically all that stuff. So you kind of confine gallium arsenide, little dots of gallium arsenide inside aluminum arsenide. That's a artificial heterostructure quantum dot. So and you can play all those games, and you modify the density of states in all these directions now. But the subband concept is important, right? As you can see, and I'll actually, let me just make this point because it's an important one. If I go all the way to, as I start reducing the dimensions, so I start with 3D, and I make subbands in 2 dimensions because it's free there, and I just, as we just mentioned, the density of states will look like that. G of E, right? Now if you start with 2D, again, I mean, maybe my quantum well width and all that are kind of the same, so I'm going to start looking something like that, right? If my structure then is, this is a narrow band gap, this is wide band gap, right? Here, that's for that. And now if you go down to 1D, which we already talked about, where you have a narrow well, there, as a function of energy, the density states, how is that going to look? I mean, that's actually an important point as well. How is, meaning you actually have 1D, and then we kind of talked about that already. But yeah, how does it look now? Yeah. So you actually will have a gap here. Right? You have a physical gap in the density of states. Does that make sense or not? Right? Or not? Yeah. Go ahead. I mean, maybe not.
I'm still not too clear on it.
Not too clear. Okay. Yeah. So, see, in this region, let me explain that a little bit. Okay? And we already kind of saw the picture for that, but that's fine. So, I have this is the narrow gap material. I have maybe 3 bound states in there. Let's say 3 bound states, and this is E1, E2, and E3. And I'm asking now, what is the density of states for this situation where I have a narrow gap material, wide gap material, and electrons are moving obviously in only one direction here, 1D, right? So I'm saying now is corresponding to this, you will actually have just a discrete state, because when the electron is in this state, it is stuck here. It cannot move in the other direction, and neither can it move. Neither is it free to move in that direction. So in the density of states, which we are plotting here, I have a discrete state which is E1. A discrete state that is E2, E3, and then the moment it becomes free, it comes back to this bound state, which is kind of going as square root of energy. Remember we saw that, 1 over square root of energy. But what I'm saying is, for the first time you get a gap here, and none of the higher dimensions you actually have a gap. You only have something that's decaying or a constant, but only here you get a gap. And this is a very characteristic feature. It has become an atomic-like state, because atomic-like states are discrete. There is no continuum of them. You have artificially made an atom here. That's the meaning of it. Yeah.
You're saying it's like a carbon nanotube. Is your model? Can it go like around the outside of the carbon nanotube like that?
That's an interesting question. So nanotubes are.
Because of
yeah.
the conductivity.
Right. So nanotubes are slightly different. Let me explain with a nanotube. So a nanotube, as you know, is your hexagonal framework, right, of carbon atoms. And the nanotube is actually formed out of a graphene sheet, right? When you take it and you roll it like that and connect it. So it's actually, the electron was 2-dimensional, and now you're right. It can have winding like that, right? I mean, it can do that. But because of the geometry, because of the size confinement, it can only fit. For example, you can only fit maybe this one or that one here. Because of that, you also have ground states, but meaning you also have quantum confinement like this and all that. But in a nanotube, you're always free to move in this direction. There is nothing stopping you, from moving there. So in a nanotube, you have a density that looks just like this. This is the density just for a nanotube, and then you have a second subband. And if you make the nanotube really fat, it looks like graphene, right? I mean, it'll merge into that, right? So So the reason for this little difference is because nanotubes are made of graphene, and graphene does not have a parabolic band structure. Graphene has a linear band structure. And as I had mentioned, I mean, the band structure E versus K is very important to the density of state, so it changes the game a little bit. Meaning it takes it to a different shape. That is it. That's all really there is. Okay. So whenever you want to introduce a gap in the density of states, at least as of today, the only thing we know is to kind of go to 1D and put a well, make it a dot-like, make it atomic-like situation, and that's when you can get a gap. Yeah, Vish.
So in the 2D case,
Yeah.
for MRS2, if I put a bilayer
Yeah.
in between the two monolayers.
No, I have only one layer here. Sorry, I think I may have missed it. I have only one layer.
I understand.
Okay, go ahead.
Smaller band gap material.
Yeah.
If I put that region rather than using a different material, if I use the same material but a bilayer.
Ah, yeah. You're saying that instead of one layer here, I have like 2 layers of the same material but a very thin strip of it.
Yeah.
Yeah, I mean then.
Act the same way.
Sure. I mean it will. So this region, I mean obviously you have to figure out what happens at the edges and all that, right? But if I were to draw the band diagram, if you know the bilayer band gap, let's say it is smaller and this layer is wider, so yeah, you will probably end up getting something like that, right? And as long as you get it, all this stuff works. Right? Yeah. It's really no different from if I take, in a very similar way, I take a quantum well and in some region make it fatter intentionally, and then you actually get, that's how, for example, here. You can do that in many, I mean, even for 3-dimensional structures, you can make it a little fatter in one direction, and then that direction becomes freer than the other two. So, yeah. So a lot of geometrical games you can play, but the subband concept is very important, and the only way you can get rid of to get discrete states, meaning there's no more subbands here. Whenever you have a subband, you will always have some density of states, finite. That's the important point. Okay, so. Let me move on. Now what I want to do is introduce the concept of coupled wells and superlattices using this idea. And this you can read also in Rocket and also in Wise book, but I'll just explain a couple of things here. So here's an example where you go beyond one well. We have only been talking about one well till now, be it in 2D or 1D or different dimensions. Now what if I take gallium arsenide and take aluminum arsenide and choose U naught of 200 MeV, and then I repeat it like that. So if I have only one well, one well, let's say I have, meaning I have just this well and there's, basically it's aluminum arsenide everywhere else after that. Then and the height is 200 MeV, and let's say my ground state was at 100 MeV. You can design it by choosing the quantum well width. And this is where all the design parameters come in. Let me say that as a engineer or some company you're working in, you're like, I want the state exactly at 100 MeV. Okay, and I have gallium arsenide, so that constrains your effective mass, because once you choose the semiconductor, the effective mass is fixed. But now I'm saying, choose whatever well width you want, but give me a ground state at 100 MeV. So that you can solve. You can find out at what quantum well width will I get a ground state at 100 MeV. Right? That much you can design. And let's say you do that, and you put one well, and you have 100 MeV quantum ground state energy. Right? Now the question is, what happens if I have another one of those? So here's for example, here the example is 4 nanometer is what gives you that right energy. What happens if I have 2 wells? Separated again by, same width as the barrier, as the quantum well. Quantum well is 4 nanometer. Let's say barrier is also 4 nanometer, and I have 2 of those wells. Essentially it's as if you have 2 wells and then it's all flat after that. In that case, you see you have one ground state here in this well, another ground state in that well. So you started with 2 wells, right? But your thickness is 4 nanometers, right? You can estimate if your effective mass in gallium arsenide is 0.067 roughly, 0.067, and the barrier height here is, if I want to estimate what is my skin depth, you can do that, right? You can calculate 100 MeV, 0.067 effective mass, and you will see there is a strong coupling to the other well. I mean, the wave function leaks, and it connects to the other well now, the state in the other well, very strongly. So they tie together. Right? Because of that interaction, you have two states at this energy. If they were not interacting, they will stay at that energy. They will not perturb each other. They will not talk to each other, right? But because of this skin depth and coupling and the penetration, they interact very strongly. And whenever you have interaction in quantum mechanics, you have two states. One goes up, the other goes down. Splits. Right? So it splits into two, and here's how much it splits, for example, in this case. One of them, if you have two quantum wells, one goes to 110, one goes up by 10 MeV, the other goes down by about 8 MeV. See that? Why did it go down lower than it went up higher? Why is that? Can you think of something? Meaning, why is the lower energy a little smaller than the higher energy? And this is actually a characteristic feature. It always happens. There's an asymmetry in it, and that has to do with, if you have a high energy, remember it penetrates further, right? The coupling is stronger. If you have low energy, it penetrates less. Think about it. That's exactly the reason why. The barrier height is different for different energies here, right? And therefore the penetration depth, the coupling is all different. Right? So therefore, when it splits asymmetrically, and it goes like that. Right? Now you couple three wells. What's very interesting is whenever you have an odd number of wells, there will be always one state left at zero that will not interact. So zero level state, and then the other two split like that. And then you keep adding more and more. And what happens is, if I have let's say 1,000 wells like that coupled to each other, the energies kind of go up here and merge into what you call a subband. So it's formed like an artificial crystal in that direction, right? In an artificial crystal now, right? And that's called a superlattice, and this is called a mini band of a superlattice. What is that? What does that mean? Remember, the atoms inside here have a lattice constant of 3 angstroms or something like that. But if your electrons are moving in this direction, their periodicity is not the atomic lattice constant. The periodicity they see is 8 nanometers, different lattice constant, right? It's an artificial lattice, which is why it's called a superlattice. It's something bigger than a normal lattice that you have, and the minimum energy of electrons that can exist in that region is here. It's not at 0 eV or 0 MeV. It is at whatever that is, about 86 MeV above that. And then and then there's a band here, and then there's another band there, and so on, for motion in this direction. Okay, so what you have created here is an artificial material which is neither gallium arsenide nor aluminum arsenide, but somewhere in between. Okay. So this sort of a material would be called a digital alloy. So it's not a random alloy, but called a digital alloy. So let me explain that aspect. So its band gap is band gap of gallium arsenide plus a little bit of this here, which is one state. Okay. And so these are called digital alloys, and as you may imagine, it has quite a few properties that are similar to a normal alloy, and quite a few that are different, and you can actually use them in both ways. So as a digital alloy. Okay, so let me just point that out. Okay, so superlattice and digital alloys, and this is, as you can imagine, you're designing an interesting sort of material. If you remember, if I look at the the lattice constant versus the band gap picture, you had kind of aluminum arsenide as an example, and then you had gallium arsenide here, and that was like 1.4 eV, and this is like 2 point something. Okay, I forget exactly what band gaps. And what we're doing now is we are taking, a structure where, it's this gallium arsenide, and then aluminum arsenide, and gallium arsenide, aluminum arsenide, and it has all this variation these are the conduction band, let's say of aluminum and gallium arsenide layers, right? And then it kind of repeats throughout. So if it was only gallium arsenide, this would be the band edge. If it was only aluminum arsenide, that would be the band edge, right? And then you have similarly your valence bands out here, right? So I'm just not sketching that, okay? But now you have a superlattice, and you have two design parameters. One is the well width here, let's say, and the other is the barrier width. And by changing the two, you can control where will be kind of the minimum energy state, which is kind of formed a mini band. Remember, they kind of merge many of these states. If you have 100, then there'll be 100 states within that little band here. They merge. It's called a mini band. And so that energy has kind of merged, and this is kind of the minimum energy band that's allowed now. Similarly, you'll have one for the valence band, which will be like that. And so for all experiments you could do, when you probe it, your band gap will be like that. It's not going to be of gallium arsenide, neither for aluminum arsenide. It's going to be somewhere in between. So what you have done is, this is so you have created an alloy in some sense, which is an intermediate state somewhere like there, by choosing carefully what is LB and well and barrier width. Right? And by changing the two, as you can imagine, you can move from here to there. You can choose any of these energies now. Right? Makes sense? I mean, clearly, if well width was infinite and barrier width was 0, or something like, or if LP was much smaller than LV, you'll be like here, so everything is gallium arsenide. But it's actually even richer than that. And the other way to create this alloy would be, when you're growing the material, every layer, in this structure has, say, let's say this is aluminum 0.3, gallium 0.7, arsenic. Let's say this point, it has 30% aluminum. 30% aluminum and much more of gallium. It's closer to gallium, right? So that's one way of potentially creating it, right? As you can see, I mean, on an average, I must have like 7 layers of this and 3 layers of this, for example. I mean, not necessarily. You can have less or more or whatever, right? You can design in any ways, change the widths and all that. But here you can also have a situation where every layer has 30% of the atoms in every atomic lattice here. 30% of the atoms are aluminum and 70% of gallium. They're completely randomly oriented. I mean, when you grow the materials, you only provide 3 aluminum to 7 gallium atoms in every layer, right? So that's called a random alloy, right? And alloy, right? So does that make sense? I mean, every layer has this. So there you don't have this sort of discreteness of the lattices and every unit cell, but what you have is some sort of a compositional non-uniformity over every lattice constant, right? So every lattice goes. If you're sitting very close to gallium regions, it will look like gallium arsenide. If you're sitting very close to aluminum, it will look like aluminum arsenide. But on an average, it will always look like a 30% argon. So that's it. And what is very interesting is whenever you measure the band gap of something like that, and you have a straight line, and the straight line law is just called the Vegard law, right? I think you have seen that in many forms. I don't want to somewhat empirical law saying that if certain conditions are satisfied, your lattice constants, your band gaps, effective masses, all that stuff, you can do a seesaw rule. I mean, x times this plus 1 minus x times that should be the property of the alloy, right? I mean, if x is the composition of the alloy, and you can actually beat Vegard's law by going to a digital superlattice. You can completely change the game. That only applies most of the time for a random alloy. And in general, what happens in a random alloy is, if I have two materials with slightly different band gaps and all that, what you have is Vegard's law will tell you that the band gap or the effective mass or something like that should go linearly. But if you actually measure the band gap of an alloy, which is, let's say this is B and A, somewhere in between, you always have something which is called the Boeing parameter. It always is lower than that if you look at band gap. If you form a random alloy, always low. Never higher. Never this way, always low. And this is typically, so if I were to write the band gap as a function of composition A, and Vegard's law says that, well, find the band gap of A, you have so the material we're looking at is AX and B1 minus X. That's our compound semiconductor alloy. Okay, does that make sense? This could be aluminum arsenide, gallium arsenide, aluminum nitride, GaN, whatever, whichever way you choose. So I have two components, band gap of one component, and its composition is X, so you get a X, band gap of the other component, which is B, times whatever fraction it has. So that is Vega's law, right? What I'm saying is, in reality, when you do experiments, there's always another term here which goes as X, times 1 minus X, sometimes some other higher order terms, but this is always negative. Always. Yeah. And the reason for that microscopically is well understood, because if you look at it microscopically, if I have an alloy which is 30% aluminum and 70% gallium and arsenic, for example, then microscopically your band diagram is kind of going between aluminum arsenide and gallium arsenide, and then at the atomic scale it's hard to justify what an atomic scale band structure looks, because band structure is a crystal property. It depends on extent. But even if we kind of think of it this way, that locally it's like gallium arsenide here and aluminum arsenide here, 70% of the time it's like gallium arsenide and all that. And if you throw electrons and holes in here, it's not going to see an average, but it's probably, you can see why the gap is always lower. It's always going to prefer to be in the lower region, always, right? And the holes will always prefer to be in the higher region. So it always, the gaps always look, obviously there's quantization and all that stuff that destroys this picture, but no matter what scheme we come up with, we cannot ever explain a higher part. We can always explain a lower part. So, basically it's an energy minimization picture that always explains, okay? But this sort of behavior, you can eliminate this disorder, and because of disorder when you do luminescence, there'll be a certain width to the luminescence. It's not completely sharp, but there'll be a width because there are different regions of different quantization and all that. And so the alloy regions will always have typically a broader line width when you have light emission from it, compared to a binary which will have much sharper line width typically because of this disorder of the alloy. If you go to a digital alloy, you can make something like this way, but you can also make it sharper because that is completely controlled. So that's another game that you can play in compound semiconductor devices. Yeah. Okay, so anyway, that's what I want to say about digital alloys and superlattices. Sorry, there's one more thing I want to say about superlattices, which is what do you think? For example, let's just look at the conduction band here. How will the density of states of a superlattice look? We already talked about one quantum well and quasi 2D system and all that. But now I'm saying I have, a whole layer, of, this sort of gallium, narrow gap material, wider gap material, and they're alternating. How will the density of states of this structure look? So I'm going to plot density of states versus energy, again, function of energy. How will that look? So that's a little trickier question, but remember, if you had only one well, it looked, so the ground state, let's say here, it looked like something like that, right? If you had only one well, right? It goes as every 2D subband, because free to move in that direction, but not free to move in this direction. And then you kind of, after you go and hit the conduction band as the top one, you kind of merge with a 3D sort of density of states, continuum. That's how it looks. But here, what has happened is you have many of these states, right, that are, this direction is now not completely confined anymore, right? You can move, right, by coupling between the wells. Because of the penetration depth, skin depth, you can move, couples. So it has formed a mini band here, and you can actually move within this mini band, right, in the z direction. If you do the right ones, and this is done in Weissbuch's book, by the way, so not in Rocket, but Weissbuch's book. So I've referred to that, and also it's up on the slides. You can calculate, and the miniband, there's a most simple picture of the miniband is your energies of the miniband are going to look like, a certain hopping term, which takes you, essentially you have some skin depth here, skin depth there. If you, multiply that with the potential barrier energy and all that, you get a certain hopping energy term, just like the tide binding hopping energy. This is that. Sorry, it's not like it is exactly that. This is the tight binding hopping energy, and then you get a cosine of sometimes a certain d, where d is the period of this structure. So it develops a band in that direction. And this is the meaning of a band. It develops, because there are all these energies that are coupled and they can move, develops a band in that direction. And in the x and y direction, they're free, right? They're free. So, oh, now we've got some food for you guys. So, yeah. Good, yeah. Yeah, so just give me 5 minutes, we finish this and can get going on that. Yeah. Thank you. Yeah. So essentially, you can see now the energy will be because of free motion in the xy plane, but in the z direction, it's not really quantized anymore. It has formed a band. So it's going to also have a qz or a kz sort of thing here, okay? Just like it has. So essentially, this part is just a square k square by 2m. And now you take this and you take your density of states. What all that it's going to do is, remember there were these sharp features. Why? Because your electron was completely bound in that direction. It couldn't move. The moment it starts moving, so essentially this part of it is going to look like the inverse of cosine, and that part I'm going to leave it to. So essentially you turn this upside, reverse, and you get a broadening of this part, which will look like, inverse cosine. It'll go like that. And then it will, it's going to, kind of do that to your band structure. It comes directly from here. Nothing fancy. Remember, if you had only one well and no coupling, it was basically a unit. It's like the energy. There's only one energy. It's kind of a discrete state for you, right? And that's why you got this. What you're doing here is kind of integrating over the number of states. If you have a discrete state, you got a jump, and that sort of picture. Just as a rough picture. But now, because of this picture in a superlattice, you're going to get these broadenings, and it'll look like that feature. So I just want to bring that up, a calculated one, and have a look at it. So exactly, the picture at least is, if an electron is moving in that direction, the quantum states now inside this region are allowed like that. They form these mini bands. You can see there'll be, for example, here there'll be 2 mini bands. Because of each state, they have lower miniband and upper miniband. Interesting aspects of it. The miniband energy here will not be symmetrically split because of coupling. Similarly, the width of any miniband, you can go back to your graphene problem, is like 4 times the hopping energy. 4 times the hopping energy, roughly. Hopping energy of this lower state is going to be, the hopping would be much easier, much tougher, because the barrier height is much larger. So the bandwidth of this miniband is smaller than the bandwidth of the upper ones, and all that stuff. They're all connected. Okay, so now we go to superlattices. Here's an example, some structures. This is a gallium arsenide-based heterostructure. That's on anyways, some of these are like a couple of nanometers. So this is a single heterostructure. This is the single quantum well, multiple quantum well, type 1 superlattice, which again I just mentioned. You can kind of start doing anything you want now, coupling wells and choosing different sorts of band offsets and all that. And here are the energy. This is, by the way, from Weissbuch's book, so please read up that chapter. It kind of doesn't derive everything in detail. It kind of gives you the formulas pretty much, but I think hopefully you can know where it comes from. So the energy when you have coupling between wells goes as 2 times t, which is the hopping integral, times cosine, and therefore minus 2t to plus 2t is 4t. So that's the bandwidth of that mini band, and this q is only in that direction, and transport in that direction. And then what was I saying? Yeah, this is what I was just trying to show you. that this is a calculated density of states. If you have single wells which have no coupling, you have densities that look like that. Because of the superlattice, which allows motion in that direction, you get this sort of thing because of the cosine term that appears in the energy now. Okay. And so it smoothens out some of these edges, and that's what happens. So okay, the other point here, I think this is something I'm probably asking you to do. So if you have only a single well of a certain height, say 300 MeV or 500 MeV, whatever that is, and you calculate what are the bound states allowed if you have a certain quantum well width in angstrom. If I have 100 angstrom width, here's one bound state, here's another, and then you have your, this is the height of the quantum well, and there's kind of nothing above that. If you have 40 angstroms, you have 1 and 2, and then there's nothing above that. I mean, that part is, it has a barrier height of 0.4 electron volts, and the quantum well width is changing now. The middle lines here are for a single well. And this is something essentially from that picture of right hand side, left hand side in a section. That's what you get. And this is you're going to do in your second assignment. This is a problem. I asked you to plot this. Okay. But now if you have multiple quantum wells of the same, if you keep the barrier width and the well width the same, but if you have an infinite, then if you have very thick wells, 10 nanometer apart, your waves die, right? I mean, the skin depth is very small. So all you get is the same energy, but there are, if you have 100 such periods, you have just 100 times that. It's just copies of that. There's no interaction. Right? But if the wells get closer and closer below your skin depth, right, then they start interacting in uniform bands. So the 100 states here split into a little band, and they get stronger and stronger, and this is the mini band. This is the picture. So this is by Leo Isaki. He's a Nobel laureate, they calculated this. They created some of the first artificial superlattices, gallium arsenide and aluminum arsenide. At IBM, not too far from here, and they observed a lot of very interesting transport properties and all that in these superlattices. So okay, so I think this is probably a good point to end the class today. But this is a plot. I have asked you only to do the single well structure, not the multiple wells. But with the multiple wells, I hope you can see what we're talking about here, right? This energy broadening is giving you this little thing here. But remember, all the energies in between them are really actually allowed because of lateral motion, right? Because of motion in the other two direction, which is why you have this flat part of it, right? That's what we mean here. Okay, so that's the meaning of this whole picture. And this part, make sure you understand it. If you have any confusion, please ask me questions, because many times this is lost in the translation or whatever you might. This part of it, that density of states, it looks like there's no energies here, but if you actually have created a heterostructure which is two-dimensionally free that way, all these states are still allowed if the electrons are moving very fast in that direction. It's not really a gap. No, it's a gap only if this is a 1D structure and it cannot move in the other two. That's the only case when you have a gap. Okay, so yeah, this is a good point. This is a good place to end. You may say that, when I reduce my density of states to 1D, I get a very sharp spike, and I have higher density of states. It's wrong, because a 1D state has less number of atoms, therefore it has less number of electrons. It will always have a less number of total density of states. But the arrangement, the spectra can change. You can have very sharp peak here and a little bit there. So this is it just came out in some of the journals, but this is actually true. The total density of states really, as you increase the dimensions, the total density of states increases, but then its shape can change. That's the shape of it can change, but the total always is higher in a higher dimension. Okay, yeah. That's another picture you should keep in mind. Okay, so what we'll do next time, which is on Tuesday, is start on. So there are quite a few things. I'll come back to some of the more details here, especially optical properties and such things like that, and transport. But as far as the material part of it goes, and some of the ideas I wanted to cover about design of these heterostructures, and how quantum mechanics plays, what sort of role does it play, I kind of captured at least most of them till now. And then a lot of it now will be about design and how do you actually use it. You're going to use these formulas and all that to calculate some of these things. The next thing I want to do is motivate what's the need for some of these heterostructures from a device perspective. Okay? And that's we're going back and forth in Rocket's book, but this is chapter 3 in Rocket's book, so that's what we're going to do next. But this I will go through fast because this is not a device physics course. I'll show, what is a p-n junction, what is a transistor, what's a laser, okay, and then say we need this material, this device needs this sort of material design, this device needs that sort of material design, and then from there we go back and say that, go back to all this stuff that we talked about. How do we, how does the device aspect of it dictate what sort of materials should we choose, and then make the connection there to the compound semiconductor. So that's what we're going to do next. Okay. So so on Tuesday we're going to start on this. So if you have time, please read up. And your assignment I promised to post on Thursday, but it's taken a little longer. I think maybe either tonight or tomorrow morning it should be up. So your next assignment, your second assignment. Okay, good. Any questions? Or probably. Yeah.
When is it due, the assignment, you said?
Next assignment? No, it'll be posted. And then when is it due? I'll find a good date. Yeah. Okay, good. We'll meet on Tuesday, and please have some of the pizza that I think Bish arranged.
Thank you.